mic test on YouTube.
Okay, well, welcome here. I said I would try and talk a little bit about the history of physics. That's particularly pertinent to me right now because for the last several months I've been very busily working on physics and actually have some super exciting things that I figured out that I'm hoping to talk about early next week. So consider this a precursor of some of the things that I want to talk about next week about sort of progress in understanding fundamental physics. What I wanted to do here today was to discuss a bit some of the history of physics as a field and how we've kind of got to where we are now. So Let's start at the beginning. The question is, how does the world come to be the way it is? And in every culture, there have been creation myths. Some of the more extreme ones, the world is made on the back of a turtle and it's turtles all the way down and so on. But there's always a creation myth. And when it was written in the terms of explanations which were available at the time. And some of these creation myths seem to us these days mere analogies, allegories, etc. Actually, they often have quite interesting things to say if one sort of is prepared to translate them back into the sort of explanatory framework of the time. But I suppose that if we look at ancient civilizations, the ones about which we probably know the most in terms of their thinking are the Babylonians and the Greeks. Both of them had sort of important precursors to physics, and we should start off talking about those. So as far as the Babylonians were concerned, first of all, the Babylonians kind of did one thing very right, which was that they wrote down things on clay tablets, and those clay tablets survive. And let's see if I actually can pull it out. There we go. Yeah, sample clay tablet. There we go. That's a little Babylonian tablet. Not a very exciting one. It's just one I happen to have. That's it's a barley contract about somebody selling barley, delivering it in different months, and so on. But this thing is about 3,000-4,000 years old, and what's neat about Babylonian things is that they've survived, and other civilizations that wrote on other media didn't survive. So what do we know about what the Babylonians did in terms of physics? They had astrologers who would try and predict things. They would try and predict where planets would be at a certain time in the future, whether it would rain tomorrow, who would win or lose a battle. Turns out they were right, that there's a systematic way for scientists, in effect, to predict where planets will be. There's not such a systematic way to predict whether it will rain tomorrow, and there's not really a good scientific way to predict whether a king will win or lose a battle. So it's kind of interesting to see that in those times, it wasn't clear which of these would be the relevant thing. But they studied a lot astronomical phenomena, and they had essentially an empirical theory of lots of things about the motion of the moon and so on. They had pretty elaborate mathematical calculations that gave essentially formulas in terms of what we would today call a sort of a primitive version of Fourier analysis that described the motion of the moon, and they would keep data about that over the course of hundreds and hundreds of years. And that's how we know, and some of the ancient astronomers knew things about eclipses and were able to measure all sorts of features of the heavens based on the records that the Babylonians had kept. But the real tradition, I think, in Babylon, starting maybe 4,000 years ago, was this kind of empirical tradition of let's observe the heavens, let's fit the data, let's make what amounts to a mathematical formula for what we see, and that's what we talk about. Now, maybe they had more kind of conceptual things, but they didn't. Those were not recorded. So, in a different tradition, there was kind of the Greek tradition of thinking about things, which was very much more of a philosophical tradition, very much more of a theoretical. We can come up with ways to understand the world just by thinking about stuff. And, from early times, like folks like Pythagoras, 500-ish BC, was thinking about sort of, can we use numbers to explore everything? And he didn't really make a distinction between numbers to understand musical harmony, numbers to understand kind of the soul, numbers to understand the physical world. It was just like there's an abstract framework with which we can think about the world. That was kind of the meta thing that he was thinking about. Well then, for particularly the pre-Socratic philosophers, 400 BC, things like that, people like Democritus and so on, they were very big on let's just have a philosophical foundation for how the world is made. And Democritus famously thought about atoms, atoma, as these indivisible units from which the world will be made. And I think the most important thing that we see from some of this early philosophical thinking about the world is this idea that, yes, the world can be made of lots of, for example, identical objects, and there's kind of a formal theory of how the world might be made.
Now, there were thoughts that, maybe the world is made out of lots of little platonic solids. Conveniently here are a couple of convenient platonic solids, in this case made out of wood rather than out of the stuff the universe might be made out of. But kind of there was the idea that, one of the 5 platonic solids might represent water, one might be fire, things like this. And that somehow there was a way to explain how the world was made in these kind of formal, essentially mathematical terms. Well, I suppose a lot of kind of the wisdom of the ancients was passed down to more modern times through the works of Aristotle. I sort of view Aristotle as the great cataloger. He would write lists of animals and plants and causes of things, structures of arguments. That's what turned into logic. And he also had kind of a sort of a catalogue of the way the physical world works, and had sort of explanations based on kind of pure philosophy of how to think about the way the physical world works. So that was kind of the tradition of the things that it's like we can figure out the world just by thinking about it. I think that one of the more interesting examples of that, a person called Lucretius, Roman person, maybe 60 BC, who wrote a book called On the Nature of Things, fairly general sounding title. But he was trying to understand how the world works and how one could put together a thing like the world. And he had a kind of an interesting analogy, which I like very much. He said, maybe the world is put together from underlying elements like atoms, in kind of the way that we might put together a sentence out of words with a certain grammatical structure. So it's kind of a way of describing a formal structure through which the world can be built from sort of underlying elements. And I think I think he was kind of right about the way it would work. He didn't have any of the tools. He didn't have computers. He didn't have all these kinds of things to work with and to think in terms of. But that was kind of an interesting idea. Of course, at the time, there were little computers. There were mechanical computers like the Antikythera device, which was found in a shipwreck. It's this sort of lump of things with a bunch of cogs. It's a surprisingly elaborate mechanical computer. Actually, I think Cicero mentions the existence of such a thing. We don't know how common or not those were in the ancient world, but in a sense, this clockwork computer type idea did exist in ancient times. At least we have one sample of its existence. So it's sort of interesting that what might have emerged if kind of computation had become more widespread in those times. It's worth understanding that this notion of sort of the clockwork way of things working is not that different from the mathematical structure of the way the Babylonians thought about kind of their explanation of the positions of planets and the moon and things like this. Well, okay, so in terms of ancient times, another kind of tradition of another sort of thing in ancient times was the development of mathematics. And mathematics had been partly developed as sort of a practical thing in Babylon for doing commerce, for computing financial kinds of things, for doing land surveying. That was kind of the origins of arithmetic and of geometry. But it kind of reached a different level of kind of philosophical significance through the work of people like Euclid, maybe 300 BC. Euclid tried to axiomatize mathematics. He tried to say, these are just things that we can say are true, that we can then build up as a purely logical matter of deduction, all of the things that we might know about, for example, geometry. And it was completely unclear at the time to what extent like physics might be axiomatizable, and to what extent the statement that Euclid makes, two parallel lines never meet, to what extent that was a statement that was sort of a fact that must be true about the world, that was somehow associated with physics, or something that was merely a mathematical assertion from which you could prove things. And it really took a long, long time before sort of this distinction between physics, things that happen to be true about the world, and mathematics, things that are sort of deducible by pure thought, could really be distinguished. And in fact, I would say that in very modern times, we maybe are almost back to the point where we might be able to turn physics into a branch of mathematics again. But that's for the future. But in any case, this tradition of kind of geometric reasoning and so on that Euclid practiced, and that would very much fit in with the kind of Greek tradition of let's figure out everything by pure thought. Now, there was actual physics done, like Archimedes, 250 BC. He did actual physics. He computed things using mathematics. But I think that he wasn't really in the let's understand how the universe is really constructed. He was more like, well, it's kind of obvious in some sort of Euclidean, geometrical, axiomatic way that such and such a thing is true about things in the world. Let's just compute how it works. And he was able to compute all kinds of things about volumes of solids and things like that, and connect some of those things to physics with things like, his principle of displacement of volume by, figuring out is this gold or not, by figuring out the density, by knowing that things displace their own volume of something like water. Okay, so the in terms of other things that sort of happened in the ancient world, by the time one was approaching sort of 0 AD, there were people like Hipparchus, early astronomer, who made a very nice star catalog and made lots of observations and so on. By the time Ptolemy, 120 AD-ish, was around, Ptolemy kind of put together all these observations into this thing called the Almagest, which for many, many years was kind of the standard of how astronomy worked. And the Almagest was, in a sense, not really a work of physics. It was a work of kind of Euclidean-style mathematics applied to observations of astronomy. And it was something where, in the end, he had this idea of epicycles, which were essentially came from the Babylonian tradition of let's make something where we can work out the motions of planets and things, in his case, by lots of lots of spheres rolling around on each other with certain particular sizes and particular detailed, elaborate structures that were essentially a representation of mathematical formulas. And I think that's most of what somebody like Ptolemy really cared about, was just the mathematical formulas that allowed you to predict things, rather than the interpretation in terms of spheres rolling on each other, which I'm not sure how much that was really thought about or how much anybody cared about that interpretation. I think it was much more the practical, let's see how we can make astronomical predictions. Well, okay, so then after that, I mean, for a long, long time, the works of Hipparchus, Ptolemy, and so on, most of the works of Hipparchus, I think, were lost. So it was really Ptolemy's Almagest that was kind of the standard for astronomy/physics for, more than 1,000 years. It finally got kind of, people started cleaning it up. A person called Regiomontanus was big on sort of doing a big cleanup of the sort of post, could one make the next step in physics or astronomy after Ptolemy? And really, one of the significant next steps was Copernicus, all the way in 1514, I think, where Copernicus was kind of working in the Ptolemaic tradition in terms of epicycles, and you can understand that these sort of things roll on these things, and you can understand the motions of planets that way, and so on. And you realize, well, actually, it's a lot simpler. You can make a sort of technical change in the way things work. You can make it a lot simpler if you don't imagine that the sun goes around the Earth. It doesn't really matter to the mathematics whether the sun goes around the Earth or the Earth goes around the sun. But you can avoid some technical details if you assume that the sun is at the center and the Earth is going around it and the other planets going around those. And so he kind of introduced that as largely a technical innovation very late in his life. I think what was interesting, in a sense, to me about that is that, yes, it was a technical innovation. Didn't even give better results, didn't give better results than Ptolemy. Actually, I think it gave worse results than Ptolemy's way of setting things up. In a sense, there was a certain, it started kind of a shockwave of the realization that what you think is true, like you think the Earth is stationary and stuff is moving around you, might not be true. You might be able to do something that is kind of a scientific thing and work out something which is completely marvelous to our senses. I think that was kind of, at a meta level, a really significant feature of what Copernicus did. And in fact, there was sort of much more philosophical runoff from what Copernicus did than there was scientific kind of development of what he did. That came rather slowly. The philosophical implications, I think, were in many ways much bigger. They were like science really knows what it's talking about, and it might be different than what you can perceive with your senses, but science is going to be right and your senses are going to be wrong. And that's kind of a tradition that has existed pretty much to the present day and has been sort of amplified over time. I think there's some problems with that tradition, actually, and which we may talk about towards the end here. Well, anyway, so after Copernicus, there was, well, I suppose the next sort of really big set of things that started happening were things that Galileo was doing, late 1500s. Really Galileo's, I think, big initial contribution was the idea of, you can really use math to talk about physical kinds of things. So, for example, the discovery that a parabola might be relevant for the motion of a projectile. The realization that there are things that are really mathy. I mean, things like parabolas have been discovered as algebra. They'd had kind of precursors in antiquity, but they'd really sort of come to the fore when algebra started getting developed in the 1400s and so on. The next big step was, yes, mathematics could sort of be directly entrained with physics. By the way, it had already been known in antiquity that in optics, kind of the theory of optics is very close to geometry. It's all about lines and angles and things like this. And even Euclid, for example, had actually written a book about optics, which is lost. It was something considered to be sort of almost a branch of mathematics, so to speak. So there had been tradition there of sort of mathematical things applied to ideas like optics, but when it came to mechanics, that hadn't really been such a tradition, and Galileo was kind of the one who really started pushing that. Well, then the big surprise was 1608, when Galileo, the telescope had just been invented, and Galileo sort of found out about it and improved it. There's sort of a possibly apocryphal story that Galileo was kind of a rather pugnacious fellow and quite an activist. But he was also, he got himself in lots of kinds of trouble. But there's a perhaps apocryphal story that he had sold the rights to his version of the telescope to the merchants of Venice, because they really wanted to go up that big tower in the middle of Venice that's still there and figure out, be the first person to figure out whose ship had come over whether a particular ship was going to come home or not, and look out at the horizon. And having a telescope to be able to do that was really a big advantage. It kind of has a reminiscence of modern times with high frequency trading and so on, where it's get a faster fiber optic cable to know what's happening in London if you're in New York and things like this. But back in those days, that was the merchants of Venice with the Galileo telescope running up that big tower in the middle of Venice and so on. But anyway, so the apocryphal story perhaps was that Galileo had sold the exclusive rights to terrestrial uses of the telescope to the merchants of Venice. So he had no choice but to then try using it for something different, point the telescope to the sky. Those rights were not used, were not sold. And in 1608, that's what he did. And probably the most dramatic thing he discovered was the moons of Jupiter. Why was it dramatic to discover the moons of Jupiter? Well, because it had been claimed by Copernicus and so on that the Earth was going around the sun, things like that. This was kind of like a miniature solar system that was operating around Jupiter, and it kind of also gave the sense that some of these kind of principles of physics that we kind of had an idea applied in the terrestrial domain also would apply to things in the heavens and things that were like things orbiting Jupiter and so on. So it was sort of a big realization that that these kinds of essentially mathematical type principles that had been that was starting to be applied to mechanics in a terrestrial domain could also apply to mechanics everywhere else. And it kind of was it started to speak to kind of the universality of physics across the whole universe, that it really wasn't any different what was going on in the heavens than what was going on Earth and so on. And that kind of started a chain of thinking that I guess we could say led to most modern mathematical science and a lot of modern technology and engineering and so on. So anyway, that was the sort of a big moment for science. Later on, Galileo started having I don't know, principles of describing science. And an important one was what's these days called Galilean invariance. The idea that it's really no different if you're stationary or if you're traveling at a certain speed. The laws of physics always look the same. That was important if you wanted to describe, look, the Earth doesn't have to be stationary. The Earth can just be moving at a constant speed, and it will seem like everything is the same as if it was stationary. And that's why we can't tell with our senses that the Earth is moving around the sun rather than the other way around. Well, okay. Once the moons of Jupiter were discovered, all kinds of things, for example, the fact that the speed of light was not infinite was discovered by 1670, 1680, by making observations on the moons of Jupiter. So it was already known that light didn't travel at infinite speed. I'm not sure that any great significance was put on that. It was known, of course, that sound didn't travel at an infinite speed. It came clear that light traveled much faster than sound. But okay. Well, meanwhile, there was all sorts of question about sort of the nature of light, for instance, like Snell's law, which is the law that determines how refraction works when you have a light ray that goes from like air to water. That law of that sort of trigonometric law of the angle that the light ray will take. Snell's law was I think 1620, and then through the 1600s, there were a bunch of kind of what we might say the obvious linear laws of physics that got discovered. So, for example, Boyle's law for gases, mid-1600s, Hooke's law for springs, that the force on the extension of a spring is linearly proportional to how much you extend it. It was like 1660s, I think. Then the friction law, the law of friction, that says that the frictional force is proportional to a constant that depends on the material times the normal force, times the amount of force that pushes the thing down onto the surface. That was okay. Well, welcome here. I said I would try and talk a little bit about the history of physics. That's particularly pertinent to me right now because for the last several months I've been very busily working on physics and actually have some super exciting things that I figured out that I'm hoping to talk about early next week. So consider this a precursor of some of the things that I want to talk about next week about sort of progress in understanding fundamental physics. What I wanted to do here today was to discuss a bit some of the history of physics as a field and how we've kind of got to where we are now. So let's start at the beginning. The question is, how does the world come to be the way it is? And in every culture, there have been creation myths. Some of the more extreme ones, the world is made on the back of a turtle and it's turtles all the way down and so on. But there's always a creation myth. And when it was written in the terms of explanations which were available at the time. And some of these creation myths seem to us these days mere analogies, allegories, etc. Actually, they often have quite interesting things to say if one sort of is prepared to translate them back into the sort of explanatory framework of the time. But I suppose that if we look at ancient civilizations, the ones about which we probably know the most in terms of their thinking are the Babylonians and the Greeks. Both of them had sort of important precursors to physics, and we should start off talking about those. So as far as the Babylonians were concerned, first of all, the Babylonians kind of did one thing very right, which was that they wrote down things on clay tablets, and those clay tablets survive. And let's see if I actually can pull it out. There we go. Yeah, sample.